Evolution, a process we've all been through but have yet to fully understand. You started off as a tiny little creature that couldn't talk, couldn't walk, didn't even have feet. There were many other possibilities too, but somehow nature decided you were the fittest. You were given the chance to live and do your thing in the world while a million others were discarded at the stage of concepts. Genes from your parents were selected, combined, and changed in an attempt to make you best adapted to your environment. This whole process is fascinating. How does nature decide what features give you the chance to be the best you that you can be? That's not a question I'll answer here, but instead I'll explore some of the ways in which this process was coded up into programs that can do a variety of cool things in games. These programs fall under the name of evolutionary algorithms. While there are many ways in which these algorithms can be implemented, a typical scenario works as follows. We consider populations or groups of individuals. An individual, or what could be a person for humans, is going to be one solution considered for whichever problem we are addressing. A player that wins a game, a sequence of actions to execute which leads to winning the game, a level designer which creates interesting levels for games, and so on. Individuals are represented by a genotype and a phenotype. The genotype is the genetic encoding, or the genes, which define the unique properties of the individual. For example, how risky a strategy should be, or how far into the future should a player imagine the game play out. The phenotype is then the manifestation of the genotype in the context of the problem, the behavior of the player, the levels created by a designer, and so on. To actually create an evolutionary process, we start with a randomly generated population of individuals. Genes for each individual are selected at random from the pool of all possible genes. We then evaluate each individual's fitness, or how good they are at solving the given problem, how often a player wins at the game, or how interesting the levels created are. Each individual gets a score based on this evaluation, which is their fitness score. We can then take the fittest individuals, or those with the highest scores, combine their genes and change some of them by randomly replacing some with others from the gene pool, in order to create more individuals, called offspring. After evaluating the offspring as well, we choose to keep only the best ones in our population. This selection completes the first generation, resulting in a population of individuals that are the same or better than before. Then we repeat this process for several generations. How long exactly? Well, that depends on the application. But at some point, we stop the process and choose the best individual in the final population to actually solve our problem to the best of their ability. Generally, these are algorithms used for optimization problems. They find a solution that best addresses a given problem. I've already mentioned some of these, but what do evolutionary algorithms actually do in games? Well, they can play games as Rolling Horizon evolutionary algorithms. They design levels, optimize games, game levels, game players, game strategies, and many more. Rolling Horizon evolutionary algorithms, or RHEA for short, use the ideas of this evolutionary process to play games. What they evolve is action plans. At each step of the game, they choose a sequence of actions of a particular length, which defines how far into the future the algorithm can see, which then brings the player closest to winning the game. Individuals here are therefore sequences of actions. In practical terms, these are a list of numbers where each number corresponds to an action. To evaluate an individual, a model of the game is used to simulate the effect of the action sequence. This is often inaccurate in games with elements of chance or randomness, but it can give a good enough indication of what may happen if the player follows that action plan in the real game. And with any problem, a good enough solution is often preferred to the alternative of spending more resources to maybe find something better. The game state reached after following each action plan is given a value based on the likelihood that the player will win from there. Often the game score is a good indication of this, and this value becomes the fitness of the individual. At the end of the process, for example, when the time budget given has been used up, the algorithm chooses the first action of the best plan found to execute in the game, and then it repeats the process all over again in the next game step. REA has been used for many games, and it is an area increasingly more researched in the latest years due to its ability to adapt to many unknown situations through the power of evolution, and its surprising strength in many games where the player receives little information as to its progress in the game, such as puzzle games. Many modifications to the basic method that I described earlier were tried, and many parameters controlling the decision-making process were adjusted for different environments, which include video games such as Space Invaders or board games such as Terraforming Mars. The algorithm works better when preserving action plans evolved from one game step to the next instead of starting from scratch every time, or when it dynamically modifies the length of the action plans evolved depending on the diversity of information in the environment. All modifications produce players able to perform the best in at least one game, but no single configuration of the algorithm is able to solve all given problems. If we frame the problem differently, we can add another layer on top. Array itself has a series of parameters that indicate how the algorithm behaves, such as the number of individuals in a population, the length of an action sequence, or the mutation rate. These parameters can be seen as genes themselves, so we can use an evolutionary algorithm to evolve REAs, which in turn evolve action sequences. And this has indeed been tried in two ways: optimizing parameters so that REA obtains the highest win rate by playing a game several times and trying out different configurations, and optimizing parameters to maximize the improvement in the quality of individuals in the population from one generation to the next. While these methods don't always succeed in producing better results, they can figure out how to solve some very difficult problems without any domain knowledge. Could we go another step higher though? Yes, we could. And maybe the way towards general artificial intelligence is up. But let's come back down and look at another side of the problem. To play a game, we first need a game. What if AI created the game before playing it? Typical applications of evolutionary algorithms don't go quite that far yet, but they can design game levels. We can encode an individual as a list of numbers again, but this time each gene will represent a tile on the screen, with a position in the list corresponding to its position, and the number corresponding to the tile type placed there. Combining two different levels would then take chunks from each to create a new level, and mutations would lead to changing some tiles to other types. The only thing left is then to evaluate the levels and give each a fitness score. This is a larger problem which can be addressed in several ways. An algorithm could extract features from the level, for example the distribution of ground tiles or the number of enemies present, and assign a fitness score depending on the distance to ideal values. Or several automatic game players could play the level, and statistics recorded about their gameplay could be used to determine a level score. For example, did the more proficient player win more than the silly player? Or a human could be brought into the mix to assess levels subjectively and use their expertise and wishes for the final design to guide evolution in the desired direction. Or we could even combine all of these methods. Recent work shows this in practice in a nice interactive web demo that involves Minecraft structures. In this application, you start with a base structure and work together with an evolutionary algorithm to improve on it by iteratively choosing one of the options the algorithm gives you and then letting it create more offspring from there. Generally, as long as you can define gene pools, genotypes, and phenotypes in a way that a computer understands them, you can apply evolutionary algorithms to bring some of the power of evolution shown by nature to your problems, and simply let potential solutions evolve until they're good enough. If only this worked for all life problems. Maybe soon. I'm Raluca Gaina, and I hope this inspired you to try out some evolutionary concepts in your work or in your next game.